All right, you guys are up.
Hello, we're Group 18, and we are presenting the Faster Than Darwin Microbioreactor. Group 18's members are Noah Raychek, Matthew Peters, Matthew Oye, Zabir Hossein, Stuart Rodriguez, and Abby Telhoun. Next slide. The outline for this presentation is that we are going to be going over the current products and the market as of now, and in which we're going to detail these products similar to our microbioreactor in the market today, and show how the Faster Than Darwin microbioreactor can differentiate itself from those current products. Then we'll also go over our Hedgehog concept and what our reasoning for choosing our Hedgehog concept was. This is followed by the overview of the Faster Than Darwin microbioreactor, and then we will choose a subsystem from the product itself and show analysis and results of that subsystem. Then we will go over the highlights of our product and what can come from it, what new things can come from it, in addition to a technology readiness level that shows where we're at with the system currently. And finally, we will show how much the system actually costs and what different, how much each group costs for the system itself. Moving on to our Hedgehog concept, we wanted to cover three topics: what we're passionate about, what drives our economic engine, and what we can be the best in the world at. Starting off with what we can be the best in the world at, we wanted to be the best in the world at providing the fastest cellular evolution. And what that means is through our microbioreactor, we wanted to produce the fastest results in the shortest amount of time by having the light intensity by the light intensity giving us the fastest results and faster throughput and the speediest results. What drives our economic engine? We are focused around maximizing profit and increasing efficiency in tandem with providing the fastest cellular evolution. This, in turn, will reduce the product operating costs and purchasing cost of the system itself. And finally, what are we passionate about? We want to enhance artificial biological growth by being a more efficient system than the current microbioreactors in the market today. All three of these topics culminate into our current Hedgehog concept. The Faster Than Darwin microbioreactor captures our passion for product efficiency with respect to simplicity, time, and cost. And we will achieve this by allowing optimization of biological processes and cultivations to speed up the production of various biological products. And we will move on to our market overview. So the bioreactors currently in the market today are used in large-scale operations such as culturing of yeast, animal cells, and bacteria. They aren't really used for research settings such as this one. They're used for large companies, somewhat pharmaceutical, somewhat technical, and usually these microbioreactors are not micro at all. They're actually very, very large, in large scale, and they aren't really autonomous. There's always some aspect that is manual or needs to be checked on every once in a while, and we as a group can capitalize on this lack of autonomous control with our system by improving efficiency, improving throughput, and most of all, making it easier to use and handle for long periods of time, which leads us to our product overview.
Yep. So guys, my name's Noah. I'll be going over the product overview. So essentially, to meet all the customer needs provided by the UF Biofoundry, we've created a system that's broken down into 8 different subsystems that meet each individual customer need. So essentially, the design we have created was a result of those customer needs provided by the Biofoundry. We created a device that has an overall dimension of the 4 foot by 2 foot by 2 foot. So that's obviously the maximum space that was allowed by the customer, but we have chosen to use that entire space. And then we could go to the next slide. We have mapped every single customer need as given by the Biofoundry to a performance metric. This performance metric essentially allows us to get a tangible number or essentially a performance goal that each subsystem needs to meet, or each customer need needs to meet. And from those performance metrics, we mapped them to the 8 various subsystems to keep track of, to ensure that each subsystem encompasses all the different customer needs, at least one subsystem does. And then from those subsystems, we've broken it down into all the different features that each subsystem has, so we could tie them back to each customer need. And then we could go on to the next slide. So so the first 2 subsystems that we've kind of broken down into the biological delivery systems are the access control and liquid dispensing subsystems. So the access control, we've chosen to use a 5-axis robot arm that is capable of positioning a tool changer hub or to the desired positions within the device. Attached to the arm is the hub, as I said, which encaptures an OD sensor. It's a photodiode sensor for optical density measurements, a filter cube for fluorescent intensity measurements, and an infrared sensor for measuring the temperature within the well plate. And then the last one is obviously the liquid dispensing subsystem. So for the liquid dispensing, we've chosen to use a linear actuated controlled syringe mechanism. So the syringe essentially operates as any standard syringe, but the top portion of the syringe is controlled by the linear actuator, which allows for fluid addition or subtraction from the well plates. So the device has to it stores the fluid within the syringe tip, and then if it runs out of fluid, we have encompassed a storage tank within the device that essentially the robot arm can position the syringe to withdraw more liquid from the storage tank. So moving on to the next slide is the shaking subsystem. So for the shaking subsystem, we have chosen to use a series of vibrational motors that lie on top of a well plate holder or canonical tube holder that essentially is mounted to some vibration dampers, or just it's mounted to the floor of the device. So the vibration motors are independently controlled to induce the proper agitation of the culture to provide either oxygenation or mixing of the fluid within the well plate or canonical tube. Moving on to the next slide. So then this is our next 2 subsystems, which are the heating and cooling subsystem and atmosphere control subsystems, which are kind of lumped together within the conditional alteration systems. So essentially for this, we have chosen to use a series of thermoelectric cooling plates, which are lined on the inside of a duct, a square copper duct, which are put in place with a channel within that duct. The system has a series of solenoids placed on the right side of the duct, as you see in the picture there, which essentially controls the gas flow from a pressurized gas canister. So the system allows those solenoid valves to control the flow into the copper duct, and the flow is directed over those Peltier plates, which are the thermoelectric cooling plates, which the fluid flows over there and is either heated or cooled, and then is outlet on the left side. We've also included a fan within the design to provide kind of a suction to get the gas to flow all the way through. And then additionally, for these two subsystems, we have included a pump. So the pump's function is so there's two chambers within the device. Each chamber has two pumps on it. So one pump is used as a roughing pump, essentially, that can create kind of a suction. So it removes the gas within the device at the start of the experiment. And then the second pump is used and connected to the sixth solenoid valve. So there's 6 solenoid valves on the heating duct. The second pump is connected to one of those solenoid valves. So the pump will pump the gas from the inside of the chamber to the solenoid valve to provide kind of a circulation of the flow, so that we don't have to constantly pump in new gas to get it to the proper temperature. And then lastly, for this set of subsystems, we have a pressure release valve. This is essentially just a safety mechanism in case the pressure exceeds 1.5 atmospheres, what we selected the release at. Then moving on to the next subsystem. So the overall structure of the device, this we chose to use an acrylic material. It is important to note that it's shown as a clear image here, but we plan to purchase an opaque acrylic to stop the transmission of light into the device during experiments. And then the acrylic was chosen due to its cost effectiveness, and then material properties as well. So then the internal components within the device are accessible via the 2 doors per chamber, one on the front, one on the back, that the user can open to service the device or change out any fluids or anything within each chamber. They're sealed off by an O-ring on the door there. Moving on to the next slide, we have an electronic system. This essentially encompasses the computer control of the device, and then the user interface, which features a graphical display and then a series of buttons that allow for shutting off the device or changing the gas content or changing the temperature. And then additionally, we have limit switches within the device placed all over that provide information to the computer control if the system is operating in the proper position, or if all the shown in the picture there, we have a limit switch with a well plate. So that just ensures that the well plate is put in place prior to the experiment starting. And moving on to the next slide, we have FIOD, which Matthew will cover.
So we have the FIOD system. So for optical density, we elected to have lights underneath the well plate. So the well plate sits on a clear acrylic holder that ideally will be frosted on the bottom. So it will also act as a sort of diffuser to get some better light spread, and it'll be more even. So then attached to the arm will be a photodiode, and that'll be able to go over each cell or each well and measure the light intensity that passes through the well. So you can do it beforehand, before you do anything, and you can get a calibration measurement that you can do it however often you choose. And then for the FI, we're planning on using a 5-watt fiber coupled laser to achieve that intensity of 1 kilowatt per centimeter squared. So in the bottom left is the actual laser box. So that'll sit outside on top of the enclosure. And then right next to it's a fiber cable. So that'll run inside to the filter cube here. So the filter cube is basically it also acts as a T. So the light will go in the middle and then it can get reflected down to the sample, but then light can pass up through it again and through a wavelength filter. So you only get the wavelength you're looking for, and then that'll go into a photodiode that then you can tell the light of that. Next slide. So some design highlights versus the competition is this multiple wavelengths. So we have the wavelength of the laser, which is the 640 nanometers. And then also, two of the lights on the bottom there, we're going to be UV lights. So that way you can irradiate the sample and kill ideally some cells, or you could run it for longer and kill all the cells if you wanted to do a sterilizing effect. So you can kill some cells and ideally have them mutate faster and with different or with more genetic variety. Another is the modularity and ease of use. And then the ability that it's split into two experiments. So each side has two distinct things that are completely separate. So you can run two different experiments, and then within those experiments are two well plates that you can run as two different trials of the experiment. Or you can use the conical tubes. Those will just be in a holder that can go into the well plate. Then the next slide. This is an analysis. Oh, this is an analysis of the heating and cooling system that Stuart will talk about.
Yeah, so we wanted to display kind of the, like Matthew said, analysis of our heating and cooling system, and I guess also the delivery system for the gases needed. So the first part, we performed essentially two heat transfer analyses, and then also kind of got a depiction of what the flow looks like throughout the duct. The first analysis is here in the square cross section. This primarily was used to determine the ideal material for the outside of the duct. We opted with a copper alloy. However, so this was performed by setting the ceramic Peltier plates at approximately 100 degrees Celsius. And as you can see with the temperature gradient here, that the outer temperature is significantly less than that 100 degrees. It resulted in approximately 35 degrees Celsius, which also validated our positioning of these ducts. Since they will be sitting directly on the acrylic, it is good to know that the 35 degrees Celsius is much lower than the melting point of acrylic, which is approximately 160 degrees Celsius. And then another heat transfer analysis we used was kind of to validate the arrangement and the number of Peltier plates we will be using within the duct. It should be noted that this was performed with about half the length of the duct and also half the Peltier plates, to kind of just get a understanding of how the flow will be heated. And that's here in the bottom left. It outputted a temperature of approximately 45 degrees Celsius, which is in that median range for the desired temperatures. So ideally, this would result in that our initial duct length and also number, the Peltier plates would also would be able to achieve that, and there's roughly 44 Peltier plates within. And then here in the bottom right, excuse me, kind of give us a depiction of the flow within the duct. As you can see, there's not much mixing through the duct. However, passing through the fan, there is some mixing. It should also be noted that this simulation was run under the assumption that that fan would not be operating for the simulation, so that would just further the mixing happening of the flow. And that's also, you can also see the mixing occur here with the temperature gradient and the output, and how it kind of changes from within. We also wanted to depict another simulation we ran. We wanted to just validate the thickness and the material choice of our acrylic walls. And by doing so, we used the weight of the arm as a force pulling down on here. We got the as you can see here, it's the gradient for the displacement, and then also the gradient for the stress induced on the wall. Should be noted that according to the simulation, the maximum stress is about 2 orders of magnitude lower than the acrylic yield strength. The acrylic yield strength was found to be approximately 83.4 megapascals. And so that's sufficient. Our design, we determined that our design choice for the acrylic walls was sufficient. With that, that it's valid and that again works flawlessly with the operating system and to atmosphere control and FIOD. We're rated at a level 4. This is primarily, though these systems would need to be experimentally and a little bit further more analysis done on how they operate together as a whole with, like I said, how everything is so interconnected. These were still rated a 4 primarily because they're comprised of OTS parts that are primarily operating in the function that they were designed for, as in case the solenoid valves, those are operating as just on-off flow control. And then same with the electronic subsystem, you're using a visual display as visual display buttons to provide input and so forth of that nature. And then moving on, Zabir, I'll pass it over to Zabir to discuss the overall assembly.
Yeah, I will be briefly going over the overall assembly steps for our bioreactor. We estimated that the assembly time would be around 2.5 hours, and the average manufacturing time would be around 6.5 hours. So the first step before putting in the enclosure walls to the base plate, we wanted to assemble our OD subsystem at the bottom of the base plate and the well plates. And then we are planning to put the
Are we losing him there?
Yeah, I think he just dropped out.
Yeah, I can finish this. So essentially, the overall assembly is comprised of all those subsystems that we discussed previously. The plan is to obviously assemble the acrylic housing with all those doors and hinges on there. It's important to note that we can't add the top portion of the acrylic until the last step. So we'd have to assemble the 4 walls and base of the enclosure, add in all the components that sit within that base plate, and then attach the robot arms, fluid dispensing mechanism via the bolted connection. And then you would have to add all the electrical components and then attach the top of the device and seal it off. And then you could add the atmospheric control components with the pump and the pressure release valve stuff. And then going on to the next slide. So essentially we've broken it down here into the various costs for the system. A lot of the components that we're using are OTS parts. Those comprise of the sensors, the robot arms, and then for the raw material portion of it, that has to do with a lot of, well, there's not too many custom parts, but we purchased the raw material there for machining or manufacturing. And then the manufacturing costs pertain to the machine cost, energy cost, and all that kind of information that's encompassed within that. And then you get a total price of the microbioreactor just under $9,000. And I'll hand it over to Matthew O.
There are a few features for why our design should be chosen that have mostly been outlined in our design highlights versus our competition. The first one is the affordability and modularity of our design. It leaves just over 10% of the allowable budget remaining and is composed mostly of OTS parts, as shown. The budget distribution, the remaining custom parts are bulk material and are such relatively cheap and not very complex. They're pretty simple and cheap to manufacture. The second reason is the intent behind our design specialty, the use of a shorter wavelength to kill off cells and rapidly mutate the culture. This feature allows our design to attain cell mutation at a higher rate than other available options. Our final selling point is our bioreactors' dual isolated chambers that enable the simultaneous performance of multiple experiments. Next slide. The conclusion. So yeah, this has been the faster than Darwin microbioreactor and is available to be prototyped in EML4502 starting next semester. Our design meets all the provided customer needs, and we hope that you will strongly consider our option moving forward. Thank you to Northrop Grumman and Cummins for sponsoring this project. We will now begin taking questions.
All right, thanks guys for the presentation. Do we have questions from the panel?
Can you guys go back to that flow analysis slide? Where is the gas that's coming into this flow analysis coming from?
So that's just set as like an environmental pressure in the SolidWorks flow sim. So that's just ambient pressure is always there.
Okay. It appears like you have a solid wall and you're pulling air through a solid wall,
Yeah,
which as far as I know is impossible to do.
I mean, as far as the flow sim goes, it does kind of do that, which I mean, to do the SolidWorks flow sim, you'd have to put a lid on it anyway. So I mean, it would still look like a solid wall, but yeah.
But it wouldn't be an actual solid copper wall. It would be the solenoids. It would be the flow sim's ambient lid barrier that is.
So another, I think another thing that might go along with what you're saying is that I used the perforated holes to do that. So it has kind of imaginary holes in it to draw air in.
Okay. But what is that? What in real life? What would that?
So in real life, it would be the solenoids.
Okay, so it's so the only gas flow into this is the gas from the solenoids.
Yes.
Yeah. So the system regulates the pressure or the gas flow through the solenoids into the duct there. Yeah, but to set up the flow simulation, you have to have an internal closed geometry. So that's why it's kind of shown like that.
Got that. So then once my system is at the correct gas ratios, how am I going to continue to heat up my environment?
So that's where the additional pump was. I think we talked about that further up, but there was an additional pump in the actual environment that would take the air out and put it through the 6th solenoid. So we'd be able to recirculate it.
Okay, so there's a recirculating pump in there.
Yes.
All right, cool. Yeah, I must have just missed that then when you guys talked about it.
I have a question. I think I've asked you guys this before, but how do you intend to manufacture the heating duct?
Yeah, so the heating duct is right now it's intended to be a cast duct. That piece on the end, it's just like a diverter. So we'd manufacture that cast copper duct with the channels inside. So the Pelletier tiles have like a slight groove in them that would slide along the channel. So If you need to take them out, you just have to slide all of the tiles out for like one wall.
Okay.
While we're here, you guys said that the fan isn't turning in this simulation, but is it actually in there, or did you guys just sort of add it later so that we
No,
could see?
So the fan is actually in there. So it's not actually rotating. Now there is a SolidWorks imaginary fan at the end. So using a fan curve that SolidWorks had, so it pretends there's a fan actually rotating there, but not physically in there. So it's sucking it out at a rate a fan would, but our actual fan is stationary.
Okay, so hang on, let me see if I follow this. So I'm gonna, if it's okay, annotate your slide here just a little bit. So if I'm hearing right, there's actually where I've drawn that kind of red box. That's where you've placed the outlet fan boundary condition.
Yeah. So that's where SolidWorks was treating the fan as.
Okay, so hence the yeah. I'm trying to reconcile, because this is these are temperatures, right? This is not a velocity profile, or is it? I think these are temperatures, aren't they?
No,
Yeah,
these are temperatures.
temperatures. Right. Okay, so I'm just trying to reconcile the temperature, because there's some elements of this that I recognize, right? There's a thermal boundary layer that grows up here and grows up here, and it's kind of more or less symmetrical. But then isn't there a big, like, maybe it depends on how fast you're pulling the air through, but my intuition, which is often wrong, but still, like, why is it cold right there? Like, shouldn't it be hot? Because isn't that a stagnation point where the thermal boundary layer would grow and just heat up the air in that spot? Oh,
it might have to do. Oh, excuse me. I was just gonna say it might have to do with the fact that the SolidWorks model might also be recognizing the solid fan that's in place there. I'm not sure if that, but I do understand what you're referencing, that it should, in theory, start to get hotter towards that general area.
Yeah. Okay. So anyway, that might be worth checking. Again, this is just based on my intuition, and I've spent a lot of time this semester actually dealing with this exact problem for something else, fan flow through a closed duct, and so that, at least the other work that I've done, there's a big thermal stagnation point right there. So I'm like, oh, where is it in this FEA? So anyway, it might just be the fan that you've selected, or somehow SolidWorks is treating it in a weird way, but yeah, that would be worth looking at.
All right, well, be sure to check that out.
I have a question. Did you guys mention the weight of the system anywhere?
I don't think we mentioned it anywhere, but with all the material inputs and estimations for the OTS parts, I think it worked out to about, I think it was like 157 pounds. So
okay.
I think one of the customer requirements was that it's movable by one person. So I think although it's a little bit heavy, it's still manageable.
Okay. Yeah. One suggestion I might add for like the final presentation would just to be to include what customer requirements you guys met, and like if you didn't meet any, maybe spell out why you didn't. 'Cause I'm not sure that was totally clear in this presentation.
On that note of weight and it being movable by one person, do you guys happen to know what the OSHA requirement on a single person lift for weight is?
Yeah, I think it's about 50 pounds.
Right, and you're at 165. So this is not movable by one person, technically. I mean, I can carry something that's 165 pounds. Some of you guys might be able to carry something that's 165 pounds. I ain't going to be happy about it, but I can do it. But it's a violation of federal guidelines.
Yeah, and I guess that kind of ties into the modularity. I guess it can be disassembled pretty easily with the robot arms, and then.
And so that would be something just to the same point about weight, would be showing how easy is it to break down into, you know, 4 43-pound subsystems that can be easily carried by a single person. That would be wonderful.
You guys hear me?
Yes.
Yep.
Okay, cool. I think I wasn't coming through previously. So for the fluid that's passing through this copper channel, right? You're heating and cooling to maintain your 4 to 70 degrees temperature.
Yeah, that's correct.
When you're cooling, where does the heat go? Because this entire copper assembly is inside the environment that you're heating and cooling, correct?
No, but previously was internally, but we've since moved it externally, so that
Okay.
the environment.
Okay, so you're just dumping heat to the lab environment?
Yeah, essentially. Yeah, it's kind of hard to see in that side view, but in that top view, it shows they're placed on top of them, and then it dumps the fluid in from the top of the device.
Does it heat does the contact then heat up your enclosure?
We didn't look at that per se. We did see the external temperature was about 35 degrees Celsius, so we kind of just made the assumption that that wouldn't be a very large effect on the system. And then we additionally have temperature sensors within the device that monitor the ambient temperature, so the ducts can improve the cooling effect or heating effect where is needed.
All right, but if it's making contact with a top surface and that top surface is heating up now, it's going to end up transmitting that heat into my internal chamber anyways. I don't see any insulation or anything like that to separate your hot object from the environment.
Yeah, right now we don't have any sort of insulation on it, but probably should add that.
One other thing that jumps to mind is you said you're making this out of opaque acrylic, correct?
Yeah, that's correct.
What is that going to be opaque to?
Ooh.
I guess all visible light.
Is that enough?
We'd have to look into that. Yeah, we'd have to see the material properties of the components we're intending to purchase, but
I'm not worried about the components you're purchasing.
Yeah, we'd have to check the material. Yeah, we'd have to check the material properties of the acrylic to see what wavelengths of light it lets in, and then adjust as needed.
That is a great question.
Okay, are there any other questions from the panel? We've still got more here, right?
Yeah, I'm here.
Hey.
I was actually thinking about how to follow on with Tom's question. I'm still sort of digesting that. See, on the subject of opacity for the acrylic, right? So for the materials, there was one positive. Let me connect the thoughts here. There was one positive that I liked, which was, I guess you guys allow individual interrogation of each well, right? You guys had that capacity, right? You guys
don't all speak at once.
Sorry, could you repeat your question again?
Well, so it wasn't a question, it was a comment. You got one benefit, one thing that I liked in your presentation was the fact that you guys had individual wells and you had the capacity to interrogate fluorescence intensity in each well, right?
Yeah.
Yeah. Okay. So typically from a user perspective, when we say something is opaque, the reason why it's worrisome right? Or why we don't want opacity is because when we interrogate what is happening from a fluorescence perspective, we have to shoot it through the material to figure out what's happening inside the cells, right? That's why we need it to be clear or what have you. If you are, so there are things like absorbance. I think this was in the customer needs statement, right? Depending on the cell culture that you're growing, we measure how well the culturing actually happens based on the amount of absorbance that exists. So if your plate, if your materials aren't, are opaque, then we're going to get incorrect readouts. But there are ways to compensate for that, which is to figure out, to use the material properties to sort of shift everything from a measurement perspective. So the question becomes, are you planning on doing something like that? Are you compensating for material opacity? Or are you just going to say that, we're not going to worry about that, right? So you understand where this is coming from. It's coming from a customer needs thing too, in addition to just the design. Does that make sense?
Yeah, I think we can account for that by taking some initial measurements of like the light transmission through that well plate holder and the well plate or the canonical tube. Yeah, and then like you said, we can shift the readings that the sensors take to reflect the true value.
But the question becomes, how are you actually then going to be able to do that characterization, and how involved is that characterization? Right? What are all the possible scenarios that a customer is going to use it for? And are you going to be developing a shift or a nonlinear mapping that is versatile enough to handle all those scenarios?
Yeah, I think that's something we need to look into further then. Sorry, I don't have an answer right now.
Yeah, so the reason why I think that it's an awesome question is because, I think it's complicated by the fact that you have this individual well capacity, which is great because we can do different things in different wells. But, if you are growing different microbes in different wells, the ODs, the optical densities are different in each wells, which is where I was going with this, which basically means that your shifts then are going to be different. It's not going to be constant across the entire thing. Is really where I was going with this.
Just to be clear, we're not actually planning to culture different types of cultures in the different wells. We just have the ability to take different, individual readings for each individual wells. They're going to be the same culture.
So is your question related to the optical density reading?
Well, it's optical density is also fluorescence, right? Because if I have different cultures and I have different things that I'm interrogating in each well, A, they will have different optical densities at different time points. B, they will have different fluorophores at each time point too, and different things, right? So using I can envision using individual interrogation capacities to a full extent by doing multiple things at once in an experiment. But if you're going to limit me and say that, well, everything needs to be the same, then what's the point of interrogating each well?
So I guess I'm just not really sure what your question about the opacity of it was, right? So the light shines from the bottom through it, right? So I guess my thinking was that before you run the experiment, you would take baseline measurements and you would know what that's like. And then you could shift your in-experiment measurements by that baseline to get a real reading.
I see. So you're going to dump it on the user.
Kinda. They would tell the device to do it, but I guess that was the intent, is that before you do it, you would put in the baseline, you would get a baseline calibration of all of it, and then you could start your experiment.
So the way it works is that there are typically standard culture vessels that we would use in a lab, right? And I would expect these sorts of offsets and this sort of calibration done for these sorts of standard things. And I would expect, I would expect some kind of plug and play capability without having to necessarily tinker around, for each device. The other reason why I'm a little skeptical about that is, this is me putting my scientist hat on. The minute you start offloading things to individual researchers, you start getting bespoke measurements and capabilities. And when people try and report these things, it's based off of their own individual calibrations rather than a sort of generic calibration. And so all of a sudden you don't get apples to orange, you get apples to apples comparisons, right? You get apples to oranges comparisons. So the more standardized you can make your product in general, the better it is.
So I guess the problem would be what we're using to hold the well plates, right? Is we don't understand the opacity of that, right? If the well plates have like a standards for that, then we would know that already.
They do.
Okay, so then we would just have to understand what the opacity of that well plate holder is. And then if we understood that, we could then not have to do the baseline reading. Is that what you're getting at?
So what I'm getting at is that there are fundamental opacity and fluorescence intensity baselines that you should provide, or measurements that you should provide a user, and you should be able to account for different materials that could be put into the device.
Okay, so is that really more of a, okay, so that's just something we have to like test or just
analyze.
Yeah.
You don't have to physically
Okay, so it's
like do it, right? You can easily, I mean, these things exist. The characterizations exist. The opacities already exist. You already know what you're using to interrogate. So you should be able to sort of already be able to say, we can handle these materials or we cannot handle these materials.
Okay. So that's just some more analysis we should do before this became like an actual like market idea, is so we know what these baselines are for different stuff.
Right. From a user perspective, it's a functionality thing, right?
Okay.
Because the idea is that the user needs to be able to, you know, it says on the bacteria and yeast, but within bacteria, there are a whole bunch of different kinds of bacteria, and they all culture differently. Again, within yeast, there are a whole bunch of different kinds of yeast. Again, they culture differently too. And so, you know, for whatever person's experiment that they're doing, we would like to be able to at least maintain some versatility here. So whatever you can do to provide it would be awesome.
Okay. All right. So that'll be something to look into for.
Does that make sense?
Designs. Yeah.
I mean,
Yeah, I think I understand what you're saying here. I'm pretty sure. So
yeah, that makes sense. Any other questions from the panel?
No. Okay. So on that note, let me stop recording.